This conference will now be recorded.
Hello everyone. Actinide series we have already started after finishing lanthanides, and some of their properties are discussed. Now we will see some more properties of actinides, then whether they form color diodes or not, and we will also compare the actinide series and the lanthanide series, because there are both similarities as well as there is dissimilarities, and also there will be related problems. Melting point and boiling point for actinides. They have very high melting point and also high boiling point. And this is just like the lanthanides. And see, do not show regular trend with increasing atomic number. So it is true that they have high boiling point and high melting point, but there is no such smooth trend. Fine. So sometimes it is increasing, sometimes it is decreasing. So there is no such regular trend. Then what about density? All actinides except these two, that is americium and thorium, they have very high density. And in case of lanthanides also we have seen there is high density. Ionization enthalpy, that is the amount of energy we have to provide to remove the most loosely held electrons from isolated gaseous atoms. The actinides have lower ionization enthalpy if we compare with lanthanides, because in this case 5F is involved, and 5F is effectively shielded from nuclear charge if we compare with 4F. Okay, so that is why we can easily remove electrons from this orbital. So we have to provide less energy, and that is why ionization enthalpy is very less. Magnetic behavior. The magnetic properties of actinides ions, if we compare with lanthanide ions, they are much more complex. Fine, but all the actinides are paramagnetic in nature, because there is always presence of some unpaired electrons. Even just presence of one unpaired electrons is enough to be paramagnetic, but unpaired electrons must be present, and it also depends on the presence of unpaired electrons. Okay, fine. Now these 5F electrons, they are closer to the surface of the atom. So if we consider, suppose this is nucleus, and if it is 4F, obviously now 5F is far from nucleus. That means we can say that it is closer to the surface area of the atom. So obviously it will be affected compared to 4F much more by the chemical environment, because chemical environment is present in the surface area. However, not to the similar extent as do the d electrons. So it is true that 5 electrons are closer to the surface of the atom and less affected by the chemical environment. Sorry, they are affected by the chemical environment compared to lanthanides. But when we have discussed lanthanides, remember at that time we have also compared them with d orbital elements. So in case of d electrons, they are affected much more by the chemical environment. In this case also they are affected by the chemical environment. But if we compare that effect of chemical environment is high in which case? Is it d block or is it 5F? Obviously it is d block. So 4F minimum effect, d orbitals, d block elements maximum effect, and in between these two 5F will be present. So there is chemical environment effect, but obviously it is not to the same extent as we observe for d electrons. Okay. Complex formation tendency. Complex formation tendency will be high only when the charge density of the cation is very high. Okay. Now if we compare the complex formation tendency of actinides and lanthanides, they have greater tendency to form complex, and it is because of the higher charge and smaller size of cations of actinides. So charge density, that is equal to charge by volume. Now volume is directly related to size. Fine. So here compared to, that is smaller size of cation of actinides, that means this is very small and charge is high. Now what will happen? Charge density will be high, and when charge density is high, complex formation tendency will also be very high. So they have greater tendency to form complex compared to lanthanides. Okay, because of high charge density, facilitating the acceptance of lone pair of electrons from ligands, because complex formation, that is all about accepting electrons from the ligands. Okay, so if charge density is high, that is charge by volume, then obviously the tendency to accept lone pair of electrons from ligands, that will be very easy. That means complex formation tendency, that is very high. Okay, so here we have seen all these 5 points: melting point, boiling point, density, ionization enthalpy, magnetic behavior, and complex formation tendency. Okay. Any doubt? Radioactivity. Now, this point we have not seen in case of lanthanides, because this radioactivity, the question does not arise for them. But in this case, when we have started actinides, then it is already, this point is already mentioned, that radioactivity property is observed for this. Okay, and this property will increase as we are moving from left hand side to right hand side throughout the series. That means as there is increase in atomic number. So when you are moving from left to right, obviously there is increase in atomic number, and radioactivity property is also increased. Okay, that means their lifetime will be decreasing. They will not be very stable. Ionic radius. Now, ionic radius means they obviously we are talking about some cations, because if it is neutral atom, it will be called atomic radius, but it is ionic radius. So the ion M3 plus, if we consider, the size of molecules or M3 plus particles diminishes along the actinide series. So this is just like the lanthanide contraction, remember? So same observation. So only now we will say it is actinoid contraction, just like lanthanide. Color formation tendency, they also show color, and it is because of FF transition, and it depends upon the how many 5F electrons are present. So here we have a graph where R in picometer unit is mentioned in the y-axis. Look at the values: 75 picometer, then up to 120 picometer, and it is given for these two oxidation state. One is 3 plus, another one is 4 plus. 4 plus, how it is changing from left to right, that we have not seen in case of lanthanides, but in case of actinides, this high oxidation state, that is also very common compared to lanthanide. So that is why both these ions we have taken, and in both these cases there is a smooth decrease as we are moving towards higher atomic number. Fine. And obviously compared to 3 plus, in case of 4 plus, all the elements, see the range is in this zone, that is 95 up to around 80. In this range we have all the values, but when it is 3 plus, now obviously the size will increase, because oxidation state when decrease, it is from higher is the oxidation state, lower will be the size. Fine. Now it is in the range in this, sorry, up to 95 up to 110 around. So this is the trend for these two cations, 3 plus and 4 plus. Here we have some pictures so that you can understand what will be their color. The colors are compared to D block elements obviously much fainter. Okay, this is plutonium 3, plutonium 4, 5, 6, 7. So all these 5 are Pu. The neptunium 3, neptunium 4, neptunium 5, 6, and 7. So all these are for neptunium. Okay. Now oxidation state, which is very, very important to understand, because if you are clear about the oxidation state, then you can easily understand the other properties, because based on oxidation state, other properties are actually controlled. Okay. In case of lanthanides, we have seen +3 is the common oxidation state. And there is also 2 more oxidation states that are observed. One is +2, another one is +4. But it is true that +2, it is not observed for all the elements. +3 is common. It is observed for all the 15 elements. But +2, it is observed for 3 to 4 elements. And +4, that is also observed for 4 to 5 elements like this, but not for all. Okay, that means maximum 3 oxidation states we can see in case of lanthanides, +3, +4, +5. But in this case, the difference is that you can see, especially the first few members, the range of oxidation state, it is very, very high. That is, variability is very high, and maximum you can find in these 2 cases, right? Neptunium and plutonium. But though there are different types of oxidation state, but dominant oxidation state of this element is obviously +3, and that is same as Ln, that is lanthanides we have seen. Maximum oxidation state first increases from +4. Now, from +4 for thorium to +5 and +6 and +7 for Pa. So starting from AC, it is +3. Then gradually it is increasing. See, the second one is now showing +3, +4, then +3, +4, +5, and +7 and +7 for Pa, U, and Np. That means up to this. Okay. Now, but decreases in the succeeding elements. That means it is increasing in this way, but again it is decreasing in the succeeding elements. Okay. Up to uranium, that is up to this point, if we look carefully, you will see that the stable oxidation state of the elements is that one which is involving all the valency electrons. Now for AC, there is only one oxidation state, so no question that which oxidation state is stable. And then for thorium, +3 and +4. That means among these two, +4 is that oxidation state where both the electrons are removed. And what is mentioned in this third statement, that up to uranium, that oxidation state is stable, which is involving all the valence electrons. So all these 2 and 4 electrons are removed. That means this oxidation state is more stable. Similarly, when it is a third one, Pa, now 2, 1, and 2. That means 5 electrons. If you remove all the 5 electrons, you are getting this oxidation state. That means the maximum oxidation state that you are seeing for thorium, Pa, and uranium, that is +4, +5, +6. So up to uranium, that oxidation state is more stable, which is involving all the valence electrons. Then the next one, neptunium, it forms +7 using all the valence electrons, but it is not the most stable state. Okay, so that is up to uranium, you can say that the maximum oxidation state is the most stable oxidation state. But after that, that is for Np, though we can see up to +7, but this is not the stablest one. The stable one is this one, +5. That means when it is in +7 state, using all the valence electrons, this will be oxidizing in nature. That means +7 is more observed, but +5 is more stable. So when it is in +7 state, there will be a tendency to gain 2 electrons. That means it is oxidizing in nature. It will accept electron from other species, and it is reaching the most stable state +5. So it is useful information that Np in +7 state is oxidizing in nature. Fine. After Np, plutonium, it also shows states up to +7 maximum. Americium up to +6, but the most stable state drops to +4 for plutonium. That means plutonium, it can show +3, +4, +5, +6, +7, but maximum stable is this one. That means if it is in any of these high oxidation state, it will have a tendency to accept electron. Similarly, americium, stable oxidation state is this one. So if americium is present in any of this oxidation state, there will be a tendency to gain electron from some other species. Okay. Then berkelium, class 4 oxidation state, total 2 oxidation state, but class 4 state is very oxidizing in nature, but it is more stable than Cl. So what it means, that berkelium class 4 oxidation state is oxidizing. So it will have tendency to gain electrons so that it can reach plus 3. But plus 4 oxidation state compared to the plus 4 of curium, that is more stable. And also compared to americium, it is more stable. Okay. Now see, for berkelium it is 5F9 7S2. So when it is plus 4 oxidation state, basically it is reaching 5F7, right? So which is stable half field configuration. So that is why its plus 4 state compared to the previous two elements, it is more stable. Then nobelium is markedly stable in plus 2 state because of its F4 configuration. So look at this. Here plus 2 state when achieved, that means these two electrons are removed, you are achieved 5F40. That means it is stable configuration. Okay. So this is all about the oxidation states. Please tell me if you have any doubt. Should I repeat any points? Now, chemical properties. The ability of actinides to exist in different oxidation states has made their chemistry more complex. So when oxidation state variability is very less, so the chemistry will be very simple. But if a particular element is showing suppose 4 to 5 different oxidation state, then it will really become very complex, right? So in case of lanthanides, we have seen different chemical properties, and we have also expressed them in general expression using Ln, right? That means there is very similarity in their chemical properties. But in this case, it is very complex, not so simple like lanthanides. Okay. Moreover, most of these elements are radioactive. That is another problem. Radioactive means there will be a tendency to disintegrate, and it is very unstable. Lifetime is very low. So studying their chemical nature, chemical properties in the laboratory is really difficult, because if some species is not stable, then how we will do experiments with this and you will gain some information. So it is really difficult. So that is why information about their chemical properties, this is really very less available. They are profoundly reactive metals in fine state and strong reducing agent also. So there will be a tendency to feed electron to some other species. That is why reducing. But we will also see some properties, though it is very complex and remember less available. They react with boiling water to give mixture of oxide and hydride. Then also react with oxygen, hydrogen, halogen. Hydrides are non-stoichiometric. In case of Ln, what we have seen, this type of hydride is formed, that is LnH3, which is very simple because Ln is having class 3 oxidation state. But in this case, they are non-stoichiometric, that is their formulas are not fixed. Having ideal formula MH2 and MH3. So these should be the ideal formula, because in these two, the oxidation state is plus 2 and plus 7. They combine with most of the non-metals also when temperature is moderate. All these metals are attacked by HCl, but the effect of HNO3, it is not so high compared to HCl, and it is because that as it is oxidizing in nature, when it will start reacting with HNO3, what will happen? There will be a protective oxide layer formation on their surface, and as a result, it will not be able to take part in reaction. So reaction with HCl compared to HNO3, it is better. We have examples with a particular element uranium. So reaction with carbon, we are getting different formula C, and temperature is also very high. Reaction with phosphorus, temperature is very high. Reaction with hydrogen, 250 degrees centigrade. with nitrogen 600 degrees centigrade. Formula is UN. That means here oxidation state of nitrogen, it is actually nitride ion, and uranium is having +3 oxidation state. So why it is important to understand oxidation state? But because suppose this type of formula is given in the question and it is asking what is the oxidation state of the element metal, I mean, then you will be able to answer. Fine. Reaction with hydrohalic acid HX, that is HCl, HBr, like this. Reaction with oxygen, this type of oxide is formed U3O8. Okay, and see, just take this example U3O8. O8 means 8 into -2, that means -16 is the total negative charge, right? So for uranium part, there are total 3, so it should be -16 divided by 3. So see, the oxidation state is really, it is not so simple. Fine. So it may be that different oxides are present together, that is mixed oxide. So from the formula it seems that the oxidation state should be +16 by 3, but it may be that they are mixed oxide. Fine. Reaction with halogen, see different types of formulas are there. UF6, then UCl6. That means when it is chlorine, X may vary 4, 5 and 6. So it may be UCl5, UCl4, UCl6, because different oxidation states are possible. So that is why formulas will also be very different. Then reaction with boron, see here also different types of formula. UB2, UB4, UB12. Another example which is with the element thorium. So oxygen, now the temperature is comparatively lesser. Reaction with hydrogen, sulfur, TH2S5, reaction with boron, air, that means in air there is both presence of oxygen and nitrogen, so you are getting that is oxygen compound and nitrogen compound. Then halogen, nitrogen, with carbon, heat, THC2. Okay, so these are the some examples, but in general we cannot express the reactions because it is not so simple like you have seen in case of lanthanides. Okay, any doubt? So now we will compare these two, lanthanides versus actinides. First point, binding energy. Binding energy of 4f electrons are higher. Binding energy of 5f electrons are lower. So it will be true. Why? Because 4f is close to nucleus compared to 5f electrons. So obviously its binding energy is high. If you want to remove electron from 4f, that will be more difficult because it is close to nucleus. Then second point, maximum oxidation state exhibited by lanthanide is +4. For example, cerium +4. But remember, +3 is the common oxidation state, and other two oxidation states that are observed, one is +2, another one is +4. So if it is asked what is the maximum oxidation state possible for lanthanides, the answer will be it is +4. And in case of actinides, because of lower binding energies, see in the first one we have already mentioned binding energies compared to 4f it is lower, and because of this lower binding energy, they will be able to show oxidation states such as +4, +5, even +6, and +7 also possible, right? So for example, uranium can show +6 oxidation state in this compound. See, one example is UF6, where 6 fluoride ions are present. Another example is UO2Cl2. Now, this molecule, it is actually containing UO2 2+. That means if you remove 2 chloride, it will be having this type of oxocation. Oxocation carrying 2+ charge. Why it is oxocation? Cation because it is carrying positive charge, and oxocation because it is also containing oxygen. So if it is +2 oxidation state, that is I am talking about UO2, total charge +2. Now in this species, what will be the oxidation state of uranium? It is very easy to understand. We have 2 oxygen atoms, that means 2 oxide. Now 2 oxide means total negative charge will be -4. So if uranium is having oxidation state X, then X -4 is equal to +2 because that is the overall charge. So X will be equal to +6. So +6 oxidation state is present for uranium in this particular compound. So if it is asked by giving this type of molecule what will be the oxidation state, then you can solve it in this way. Third point, 4f electrons have greater shielding effect, 5f electrons have poor shielding effect if we compare. Fine. Now 4f, it is closer to the nucleus. It is in general true that f electrons, their shielding capacity is very poor compared to s, p, d. But if it is asked between these two 4f, that is between these two f, one is 4f, another one is 5f, in which case it is comparatively more poor, then the answer is it is 5f electrons. Next, if we talk about colors, most of the ions are colorless. Some ions are colorless, some ions are colored, but most of them are colorless. In this case, that is actinides, most of them are colored. For example, if it is uranium 3+ state, it is red color, 4+ state green color, and when it is in this oxocation state, it is yellow in color. They are paramagnetic, but magnetic properties can be easily explained. Though remember, compared to d orbital elements, here magnetic properties are complex. But why we are saying that it is easily explained? It is compared to actinides easily explained. But compared to d orbital, it is complex. They are also paramagnetic, but their magnetic properties are very difficult to interpret. Even in that is in case of lanthanides, one formula is given when I have discussed, and if you follow this formula clearly, it will give you correct result. But for actinides, you will not see even any proper formula based on which you can determine the magnetic moment. Okay. They do not form complex easily. That means complex formation tendency for lanthanides are less compared to actinides. Lanthanides, except promethium, they are non-radioactive. So this particular element is radioactive. But here all of them are radioactive. Their compounds are less basic, their compounds are more basic. They do not form oxocation, but for actinides, oxocation formation is very common. One example we have already seen, which is UO2 2+. And neptunium, plutonium, they also form oxocation. That means they will form some positively charged species cation, but there will also be presence of oxygen. That is known as oxocation. Fine. So these are the differences. Now there are some similarities also. The lanthanide and actinide contraction. In both cases there is some contraction, and they have extended effect on the sizes in the next elements. That is after lanthanides, all the elements that you have, there is direct consequence we can see for those elements, and similar is also for the actinides. Remember the consequences of lanthanide contraction, 4 to 5 points we have discussed, and there you have seen how the post lanthanide elements are affected because of this lanthanide contraction. Lanthanide contraction is more important compared to actinoid contraction because the chemistry of elements succeeding the actinoids are much less known at the present time. So the first point is saying that in both cases there are contraction, and that is why for the post elements there is effect. But the post elements of actinoids, they are not much known. But the post elements of lanthanides, they are comparatively known. So that is why you can understand the consequence very easily, and that is why lanthanide contraction we give more importance. Though there is also actinoid contraction, but you will see that lanthanide contraction is mostly discussed, not actinoid contraction. Fine. So here we have some points which is related to the size decrease as we are moving from left to right, and this is known as lanthanide contraction and actinoid contraction. So in this table, in any of these points, because there are total 9 points we have discussed, any points, if there is any doubt, please mention. We will go to the point uses of actinides, but before that we will discuss some points that are similar. In both the series, F orbitals are filled gradually, so that is why both of them are under 4F. Both of them are called as, in general, F block elements. Depending on which F orbital is used, it will be either 4F or 5. But the common point is, in both cases, F orbitals are filled. Class 3 oxidation state is common for both. Ionic radius of the elements in both the series decreases with increase in atomic number. Electronegativity of all the elements in both the series is very low and are said to be highly reactive. So electronegativity, it has to be low because mostly they are metals. There is metallic property. So electronegativity for metals are low. So that is why here also the same thing. The nitrate salt, perchlorate salt, and sulfate. That nitrate is NO3 minus, perchlorate is ClO4 minus, sulfate is SO4 minus. So all these salts for these elements, they are soluble. But the hydroxide salt, fluoride salt, carbonate salt, they are not soluble. Okay. So this is also the common point. Uses of actinides. So here we have taken specially 4 elements: thorium, uranium, plutonium, americium. So thorium oxide, which is heat resistant property, so that is the reason it can be used in high temperature laboratory crucible, because sometimes in laboratory experiment high heat is we have to apply, and in that case the crucible that we are using, it must be heat resistant. Okay. So thorium salts are used as medicine also in the treatment of cancer. It is utilized in the preparation of fuel rod in atomic reactor. So this point is all about thorium. The next point is related to uranium. Uranium oxide based to yellow and green shading to glass. So that is why they can be used in glass preparation. It is of great commercial importance as a nuclear fuel. Its phosphate complex, as you know, in actinides, complex formation tendency is better compared to lanthanides. So its phosphate complexes are important in the extraction of uranium in nuclear waste processing. Then plutonium is fissionable material. So these terms that you are seeing here, fissionable, that means where fission is possible. So it is a particular type of reaction that we discuss in radioactive elements. So it is fissionable material. It is utilized for fueling nuclear reactor, and these are some other applications. So basically it is observed that in radioactive reactions mostly we can find the applications. Then 241 americium, where this is the mass, is valuable laboratory source of alpha particle. Alpha particle is nothing but helium-2. Okay. Now we'll see this problem. Choose the incorrect statement. We have total 4 statements, and one of the statement will be wrong statement. The chemistry of different lanthanides are very similar. So can you tell me, is this statement correct or not? Because lanthanides we have already discussed, and it is saying that chemistry of different lanthanides, there is some similarity. So is this true or is this wrong? Any idea? So chemistry of different lanthanides are actually similar. So that is why the chemical properties, when we have discussed, most of the time we have expressed with the term Ln, and that is possible because their chemistry is very similar. Then the next point, 4f and 5f orbitals are equally shielded. Now it is not possible that 4f and 5f are equally shielded, and that is also we have discussed. Fine. So the first point, that is the valence orbitals, that is 4f orbitals, they are deeply buried and not affected by the ligand field, and that is also the reason for which we get sharp band in the electronic spectra. And as these 4f orbitals are less influenced by the ligand field, so that is why they will show a very few oxidation state, +2, +3, +4. So that is the reason their chemistry is very, very similar. So this is the explanation for the first statement. So this is true. Now the second point, it is actually not true. 4f orbitals closer to the nucleus if we compare with 5f orbitals. So that is the reason that the electrons in 4f orbital, they will feel much more high attraction. So 4f orbital has more density of electrons compared to 5f orbitals, and that is why their shielding power will be high compared to 5. So this statement is not correct. So that means it will be the correct option. But we will also see why the other two statements are correct. D block elements show irregular and erratic chemical properties among themselves. Third statement is related to D block elements, and it is saying that there is irregular and erratic chemical properties among themselves. That means regular trend in the chemical property is not observed. So in D block elements, valence orbitals, that is D orbitals, they are not deeply buried like 4f. So there will be much more influence of the ligand field, and there is variable oxidation state possible. So showing variation in properties such as magnetic and electronic spectra, and also oxidation state. That means these are the reasons why their properties are irregular. That is, chemical properties are irregular. Okay, so this statement is also correct. The last statement again related to lanthanides. La and Lu, that means lanthanum, first element, and lutetium, the last element, they have partially filled d orbital. Now see, this is the electronic configuration for La. After xenon, it is 6s2 5d1. After xenon, for lutetium, it is 6s2 4f14. Here it is 4f0. 2, 1, 2, 14, and then 5d1. So this is the last element, but in both cases, 5d is containing only one electron. That means it is partially filled. So this is also true. So the incorrect statement is the second statement. Fine. Any doubt? The highest possible oxidation state of uranium and plutonium respectively are 6,4, 7,6, 4,6, and 6,7. Now uranium, plutonium both are from actinides, right? So when we see uranium configuration after Rn, noble gas configuration, it is 5f3, 6d1, 7h2, and for plutonium again same inert gas element, 5f6, no d electron, that means 6d0, 7h2. Now remember, in the slide of oxidation state, what we have mentioned, there we have mentioned that up to uranium, the highest possible oxidation state will be that state which is involving all the valence electrons. Okay, that means up to uranium, here 3, 1, 2. So if you remove all the electrons, 3 plus 1 plus 2, basically you are removing 6 electrons. So maximum highest possible oxidation state, it is involving all the valence electrons. So 6 will be the correct answer. Now 6 is present in option A as well as in option D. Then for plutonium, so these two are cancelled. So for plutonium, is it 4 or 7? Now plutonium is coming after uranium. So its highest possible oxidation state, it is not involving all the valence electron. That means highest possible oxidation state is not involving removal of all these 8 electrons, 6 plus 2. So here basically the highest possible oxidation state found is plus 7. That means though there are 8 valence electrons, but plus 7 is the highest possible oxidation state. So this will be the correct option. 6 for uranium, 7 for plutonium. Okay. Here we have some points related to actinides, and we have to find which one is correct. So actinides are all synthetic elements. Is it true? All are synthetic elements. So can you tell me whether it is true or not? Synthetic elements means which are man-made. That is, it has no natural occurrence. That means it is synthetic element. Is it true? It is not true. All of them are not synthetic. Fine. Because if it is so, then it should be properly mentioned. But we have never mentioned that all of them are synthetic elements. So this is not true. Then the next statement is saying includes the element 105. Sorry, 104. Now remember the actinides, it is ending at lawrencium, which is having oxidation atomic number 103. That means 104 is the next element, and the element is actually rather rutherfordium, but it is not included in the actinides. So this statement is also not correct. Then the third statement, have only short-lived isotope. Okay. Now it see here actinides, if we make the full statement, it is saying actinides have only short-lived isotope. So it is having the meaning that as if all the 14 or 15 elements, they are having short-lived isotope, but that is not correct. Only in the last part, that is in the second half, the members that are present, they are actually short-lived. Their lifetime is very less. Half-life is very, very low. So this is true only for the elements that are in the right hand side, but not for all the actinides. So this is also not true. In general, you cannot say that all of them are short-lived isotopes. Variable valency. Now this is true. Remember, starting from +2, you can even can have +7 oxidation state. Fine. So all actinides show different oxidation state, such as all these. However, +3 oxidation state is the most common among all the actinides. But all this range is observed. So have variable valency. That is correct. The wide range of oxidation state of actinides, why it is possible? It is possible because of the fact that 5F, 6D, 7F, all these three orbitals, their energy levels are of comparable energy. That means the energy difference between these orbitals, they are very less. And that is the reason that all these three subshells, they can participate in the bonding. So sometimes electrons are removed from 5F, 6D and 7S. Just take the example of uranium in the previous question. Here all the electrons can be removed and +6 oxidation state can be observed. That means you can remove electron from 5F, 6D as well as 7. And that is possible because their energies are very close to each other. If there is high energy difference, suppose energy difference between 6D and 7S is very, very high. So obviously now the electron will be taken from that subshell which is having lower energy. But if all of them are having more or less same energy, so electrons can be removed from all of them. And that is why high oxidation state is possible. Okay. So the last statement, this is correct. Any doubt? The actinoids exhibit more oxidation states in general than the lanthanides. You have to find the reason for this statement. So this statement is given. That is fine. We know that actinides, there is very high number of oxidation states starting from +2 up to +7. But why not for lanthanides? What is the reason behind it? That is the question. The first statement is saying that the 5F orbital extend further from the nucleus than the 4F orbital. Then the second statement, 5F orbitals are more buried than the 4F orbitals. There is similarity between these two orbitals in their angular part of wave function, and actinoids are more reactive than the lanthanides. So we have to find the reason. Now see here, if we look at the statement, option C, it is really difficult for us to understand that whether there is similarity in their angular part of the wave function or not, because sometimes it is theoretical. We cannot say much more about it. So what we can do, if we are sure about any of this statement, then we can easily eliminate the others. So in actinoids, the outermost 5f orbitals, it is true that they are away from the nucleus compared to 4f. So if it is nucleus, first there is 4f, then there is 5. So which makes them similar in energies to 6d and 7s, because 6d and 7s, they will be closer towards 5f, right? So electrons can easily, that is transition possible between these orbitals. So we can remove electron from 5f, 6d, 7. And once they reach the valence orbital, they can be ionized, leading to variability in oxidation state. Just take the last problem in the previous slide. What we have said, that variable valency is possible because the energy difference between 5f, 6d, 7s, this is very less. So actually here also the same thing, but we have to find statement from this. So you can easily eliminate C, because not eliminate, I am trying to say that keep it aside, because it is not possible for us to understand that angular part of the wave function is same or not. But what we know is that these 5f, 6d, 7s, their energies are very close to each other, so we can remove electrons very easily, right? So in the case of lanthanide, the outermost 4f orbitals, they are too close to the nucleus. Distance is less. So that is the reason actinides are showing higher number of variable oxidation state, because the first statement is saying 4f, 5f orbital extend further from the nucleus compared to 4f. So this statement is nothing but another way of saying that outermost 4f orbital too close to the nucleus. So you can say that 5f is further from it, or you can say 4f is closer to it, but both are having the same meaning, right? And second statement cannot be true because 5f orbitals are more buried. That is not fine. This is more. Okay. And the last statement, that is actually fine. That is, they are more reactive than the lanthanides. But this cannot be the reason why it is showing higher oxidation state. This is as if an effect. But we have to find reason why it is showing maximum oxidation state. So reason is the first statement. Fine. Maximum number of possible oxidation states of actinoids are shown by which of these pair. So in each option you will find some pair: nobelium, lawrencium, neptunium, plutonium, actinium, thorium, berkelium, californium. All these 8 elements, they are actually actinides. But which pair will show maximum oxidation state? So this table I have already given in the oxidation state slide. Fine. So I have added it here again so that you can understand it easily. Here these two elements, it is showing +7 oxidation state, right? That means maximum oxidation state, it is shown by these two. Fine. Np and Pu, that means neptunium and plutonium. Mixed metal is an alloy consisting mainly of. Remember, this term we have discussed in the application part of lanthanides in the last class. And there it is mentioned what is actually this term signifies. This is actually an alloy. That is already mentioned in the question, but you have to answer that it is consisting mainly of what. Now we can easily remove this option because it has nothing to do with actinide metal. Okay, and also option 4 is not correct. Next, we have lanthanide and actinoid together, and option 2, it is mentioned only lanthanide metal. Now, just have a look at the definition once again. It is well-known alloy which consists of lanthanide metals around 95%, and rest of the 5%, there will be iron and traces of all these elements, non-metals as well as metals. But mainly it is consisting lanthanide. And here there is no mention of actinoids. So in option 1, actinoid mention, it is also not correct. So only one option is left, which is this one. Any doubt in these two problems? Which one of the following lanthanoid does not form MO2, and where M is lanthanide metal that is given in the question. Now all these four options that are given here, you have to understand that first you have to find what is the oxidation state of this element M. It is actually metal in this formula. 2 oxygen, that means 2 oxide. So total negative charge -4. So total positive charge must be +4. So basically the question it is asking that which of the following lanthanoid does not form +4 oxidation state. Now remember, +4 oxidation state is not formed by all the elements. It is only observed in some cases. Have a look in the electronic configuration. For ND, it is true that all of them are lanthanides, but the configuration is 4F14 6S2, then PR 4F3 6S2, DY 4F10 6S2, and ytterbium 4F14 6S2. Now YB2 plus, that is if you remove these 2 electrons, it will have fully filled stable configuration of 4F. But further, if you want to remove 2 more electrons, you have to break the 4F14, which is really difficult, and it will require very large amount of energy to reach that oxidation state. But look at the sorry, it is also given, it is not correct. Okay, this one is the correct answer. It is given wrongly. Now, as the removal of the next 2 elements, it is really difficult. So that is the reason +4 oxidation state we cannot achieve. Okay, so which option will be correct? Any idea? Sorry, it is 4F4. Yes, it is fine. It is 4F4 6S2. So here, that is rest of YB. In all other cases, when you are trying to remove the 3rd and 4th electron, basically you are breaking the configuration 4F4. Here it is 4F3. Here it is 4F10. So it should be comparatively easier, right? But in case of YB, it is 4F14 that you have to break. So that is why this will be difficult. So which one of the following lanthanoid will not form this type of oxide is YB, and it is because of the oxidation state. The question can also be asked in another form, that is in which case +4 oxidation state is not possible. But if it is asked in that way, it will be very direct. But here it is asked in indirect form. In the context of lanthanoids, which of the following statements is not correct? So all these statements are related to lanthanoids. You have to find the wrong statement. There is gradual decrease in the radii of the members with increasing atomic number in the series. Now this is true because of lanthanide contraction. All the members exhibit +3 oxidation state. That is also true. Because of similar properties, the separation of lanthanoids is not easy. Now, if at first glance you are not sure about this statement, just go to the 4th one. Availability of 4F electron results in the formation of compounds in +4 state for all the members of the series. So it is as if saying that +4 state can be observed for all the elements, but that is not true. So this is false. So sometimes it may happen that you are not sure about some statement. Then just keep it aside and go to the next statement. So if you are sure about this, okay, then you can easily understand that this is true. So because of their similar properties, we know that though there is lanthanide contraction as we move from left to right, but still the difference in the sizes are not very high. So that is why though there is decrease, but the decrease is very slow decrease. So more or less their sizes are same. So that is why their separation is comparatively difficult, because when sizes are shaped, sizes will be comparatively similar, chemical properties will be same, so separation becomes difficult. Okay, any doubt? the lanthanoid contraction is responsible for the fact ZRY, ZRNB, ZRHF, ZRZN. Zr is common, zirconium, and another element is changing. The first statement, it is having same radius, similar oxidation state, same radius again, similar oxidation state. Remember, when we have discussed consequences of lanthanide contraction, 4 to 5 points, then you will find the answer of this question in that part. So this is the 3 series in D block, and this is the position where all the 14 elements are present. So La is having 57 atomic number, but after that there are 4 elements also. So La plus 14 elements, all are in the same group, same period, and after that there is HF. Now this is the position of Zr. So what we have seen, that as because of this lanthanoid contraction, there will be effect for the post lanthanoid elements. So for this, what will happen when you are moving from 4D series to 5D series? It is normal expected. We normally expect there should be increase in size because of extra added valence shell. But here it is observed that for all these pairs, MOW, molybdenum tungsten, technetium rhenium, ruthenium osmium, all are having same size, same radius. And why it is so? It is because the lanthanide contraction effect is still going on. So the expected increase you cannot have. So Zr and HF, these two will have same radius. But Zr and Zn, it has nothing to do with Zn. There is no effect of lanthanide contraction. Then Y? Y is here. So it is not related to Zr. And Nb, that is also not related because Nb and tantalum will have similar radius. So this is also not correct. Zr and HF. Okay. So in the entire D block, only in group 3, that is the first group, the size increase from top to bottom, that is from 3D to 4D, 4D to 5D, it is normal because there is no lanthanide contraction consequence. So that is the reason the size as you are moving from SC to Y to La, it is normal. But from group 14 up to group 12, there will be the size of 3D, it is lesser than 40, that is fine. But size of 4D and 5D, it is almost same because of lanthanide contraction. So that is why these two will have same radius. So we are at the end of the session. So regarding all the slides, if there is any doubt, please mention. So this is the end of this chapter. Next we will start another chapter. So if there is no doubt, we are ending the session here. Thank you for listening.